Hello. It is well known that atmospheric or oceanic motions are turbulent. However, turbulence is not easy to define. It relies on several statistical tools. We will not give here a basic lecture on fluid turbulence. It would take several hours. Nevertheless, we will try to give some general definitions and very simple concepts to start with. Turbulent flows are directly related to disorder or randomness. A fascinating illustration of atmospheric turbulence is provided by the famous painting of Van Gogh, The Starry Sky, which qualitatively illustrates how the turbulent swirling motion of the atmospheric boundary layer affects the light propagation. The flickering of the stars, amazingly reproduced by the artist, is indeed directly related to the atmospheric turbulence in the boundary layer. If now we consider the precise measurements of the atmospheric wind velocity at a given location, we generally get this type of signal. This curve is probably less artistic than Van Gogh painting, but you can also distinguish here rapid fluctuations of the wind speed around a slower evolution of the mean wind. These high-frequency fluctuations are measured by an ultrasonic anemometer, and it is quite simple to perform a temporal averaging to filter out the rapid fluctuations. The main hypothesis of turbulent flow analysis is that we are able to separate the non-turbulent flow from the turbulent fluctuations. If we use a temporal averaging to perform this separation, on which characteristic timescale the averaging should be done? To answer this question, let's have a look at the wind power spectrum. Here is a typical curve for wind power density. There is a large peak around 5 to 6 days, which corresponds to large-scale synoptic perturbations. A peak at 12 hours, corresponding to the night and day variations, and a large spectral gap of low energy between few hours and 10 minutes. And the last peak at higher frequency is associated to the atmospheric turbulence. All the rapid wind variations of the order of minutes or few seconds correspond to turbulent fluctuations induced by small-scale eddies or waves. The spectral gap is crucial to validate the temporal separation between the meteorological time scales and the atmospheric turbulence. We can then easily extract from any wind measurement the turbulent part of the signal. If the mean wind is expected to be predicted by an accurate weather forecasting system, the turbulent fluctuations are fully chaotic, and we can only try to estimate some statistical properties. By definition, the mean of the turbulent velocity, u hat, is 0, but not the mean of the square. Hence, we use the root mean square to build a dimensionless number which quantifies the relative intensity of turbulence. The turbulence intensity is the ratio of the root mean square of the turbulent wind over the mean wind. In the atmosphere, this turbulent intensity could reach quite large values. Typical values of 20 or 30% could be reached for low winds, and relative turbulent intensity decays when the mean speed increases. On these curves, we can see that the turbulence intensity is maximal near the ground within the boundary layer, where the vertical velocity shear is strong, while at high altitudes, outside the boundary layer, the velocity shear and the turbulence intensity are much weaker. The bottom roughness is a major source of small-scale and turbulent motion, and therefore it will have a strong impact on the turbulence intensity. For the same geostrophic wind forcing, a 10-meter square wind in this example, the wind intensity close to the ground could strongly differ. On one hand, if we consider a quite rough configuration, such as an urban area with tall buildings, the vertical extent of the bottom boundary layer will be large. The wind at 50 meters will be significantly reduced by the bottom friction. On the other hand, for a quite smooth bottom, such as the sea surface or fields, the bottom boundary layer will be confined in a thin layer close to the ground. And in such case, the 50-meter wind speed will be closer to the geostrophic winds and could reach a value up to 8 meters per second. Hence, we've seen that the vertical profile of the average horizontal wind speed strongly depends on the bottom roughness. And we could wonder if some universal curve exists for the velocity profiles in the bottom boundary layer. We plot here the mean vertical profile of an oceanic boundary layer forced by the tides. As for the atmospheric boundary layer, the bottom roughness strongly impacts the velocity profiles. And, quite surprisingly, when we rescale the velocity with the vertically average speed, most of the curves collapse on a single one. For distinct directions, ebb or flood, and various flow intensity, spring or neap tides, it seems that we get a generic velocity profile for the bottom boundary layer. The main goal of the overall session will be to understand how we can derive such a universal velocity profile for a highly turbulent flow. And the Reynolds decomposition is the first step to achieve this goal. The underlying assumption is that if the instantaneous flow is unpredictable, there exists a mean flow, in other words, a mean velocity profile, which is predictable. We show here several distinct observations of the turbulent velocity profiles along a flat bottom. And here, if we merge all these observations, we are able to extract an average profile and separate the turbulent flow from this average. However, we consider here a statistical mean and not a temporal mean. You may ask, what is a statistical mean? The statistical mean corresponds to an average over a large number of realizations of the same repeated event. For instance, you restart several times the same experiment with the same initial conditions. And the properties of the statistical mean are the mean of the turbulent velocity fluctuation is equal to 0. The mean of the product of two mean velocity is equal to the product of the means. The statistical average of a mean velocity times a turbulent velocity is equal to the product of the mean velocity times the mean of the turbulent fluctuation and is therefore equal to 0. The statistical mean of the product of two turbulent velocity is not equal to 0. And finally, the mean of any derivatives will be equal to the derivatives of the mean variables. To sum up, as far as the boundary layer is concerned, the Reynolds decomposition splits the instantaneous velocities in a mean part, the boundary layer profile, which mainly depends on the altitude, and the turbulent velocity fluctuations. The spectral gap allows us to use the temporal average to perform this splitting. Thank you.